Myself, Govind Karhale. Welcome to ICMPMA 2020, SUV 330. My topic name is Dielectric Measurement of Pulvarized Samples at 9.85 GHz frequency. So, today I am going to deliver my poster presentation on the topic dielectric measurement of polarized samples at 9.85 GHz frequency. The dielectric parameters are the temperature dependent parameters, the dielectric constant, dielectric loss, relaxation time, and conductivity of some samples in polarized form has been studied at different temperatures, that is 20 degrees, 30 degrees, 40 degrees, and 50 degrees Celsius. It is assumed that the finest crust particle of smallest size, that is 70 micron, under a pressure behaves as a solid bulk. Moisture content was measured by thermogravimetric method. The experimental values have been verified by using correlation formulas of Landau's, Leib's, Loenga, and Boucher's. The result shows that there was a systematic increase in dielectric constant and loss factor with increasing values of relative packing fraction and decrease in dielectric constant and loss factor with increasing temperature. The experimental values are very close to the values calculated from the Landau's and Boucher formulas, and there is a fair agreement between experimental and calculated values. To obtain useful information on biophysical properties of various kinds of pulverized samples, the study of dielectric behavior from microwave absorption is of great value. The dielectric properties of agricultural products describes interaction with microwave energy and depend on the frequency of electromagnetic field as well as on the bulk particle properties of the material such as moisture content, density, temperature, packing fraction, and composition. The dielectric heating effect on germination, early growth of agriculture products, improvement in nutritional quality, store grain, insect control, drying of grains, sterilization of grains, making medicine, etc., is of great importance to know the actual process at molecular level. To get some information in this direction, dielectric properties of pulverized samples were determined at various packing fractions and temperature. Now, the measurements in waveguides. There are a number of ways in which measurements of dielectric in waveguides may be made. The advantage of this method employing waveguide is that the radiation is enclosed and there is no loss of energy outside the system. The experimental method for measurements complex permittivity of materials as a function of frequency dependence on the frequency range as well as type of system under consideration. A convenient method of measuring complex permittivity of material is electromagnetic standing wave within test material or in front of the material. When sample extends over an appreciable part of wavelength, the electric and magnetic field vary over sample dimensions. In such cases, an analysis based on Maxwell's equation of wave traveling along a transmission line containing the sample is required. Apparatus employing coaxial line may be used over a frequency range of megahertz to 5 gigahertz. A hollow pipe waveguide is useful over the range of 2 to 60 gigahertz. The experimental determination of dielectric permittivity and loss rest on observations of the waves transmitted through or reflected from the length L of dielectric. The procedure followed depends mainly on whether the sample is liquid or solid and on whether the dielectric loss is large or small. If solid are to be measured, then solid may be machine or die press the wave and some adjustment of length is necessary. But the measurement as a function of length is practicable. Solid have real advantage that a window is not required for sample holder and disadvantage is that they may not fit the sample holders snugly. Recent improvements like sampling of standing wave pattern at regular intervals and automated data processing improves the experimental sensitivity In the present study, we have employed X-band microbench to measure the dielectric constant and loss factor. In this method, the length of sample column in the cell change and steps and corresponding output from crystal detector is recorded. The data obtained is used to determine the values of propagation constant in the sample. The values of dielectric constant and loss can be obtained from these propagation constant. This is the experimental setup to measure the dielectric constant. This measurement setup is having 9.85 GHz frequency. Now, the material and methods. For the pulverized sample of various particle size, we are prepared on crushing the seeds by grinder and sieves of different size. Then sample were transferred into glass bottle as so as to avoid any moisture intake. Then the label according to the grain size. For each sample, densities were measured to determine the relative packing fraction. That is the ratio of density of powder of various particle size and density of finest crust packed particles assembly. The dielectric measurements, dielectric constant and loss on these powder sample for different packing fraction were carried out at 9.85 gigahertz micro frequency and temperature 20 to 50 degrees Celsius. The dielectric parameter were measured by employing reflection coefficient from air dielectric boundary of the powder sample. This technique permits us to rapid measurements of VSWR, the ratio of amplitude of maxima to minima field strength of the wave. In this technique, heart of the measurement center around the dual three-arm directional couplers, which are packed back to back, we can measure the ratio of the magnitude of reflected and incident power, which gives reflection coefficient. Now, the values of dielectric constant, dielectric loss, loss tangent, election time, and conductivity can be calculated by using this formula. Epsilon prime is equal to lambda 0 upon lambda c square plus lambda 0 by lambda d square, where lambda 0 is the free space wavelength, lambda d is the wavelength in dielectrics, lambda c is the cutoff wavelength of the waveguide, and lambda g is the guide wavelength. Alpha d is the attenuation coefficient introduced per unit length of dielectric materials. Beta d is the phase shift produced per unit length of dielectric material. Alpha and lambda d is the attenuation per wavelength. Now, for the measurement of low loss materials, a dielectric constant, loss factor, bulk materials can be correlated with their powder from the relations derived independently by LLL formulas, that is Landau, Lipps, and Loenga. Dielectric epsilon prime S stand for solid in bracket 3 delta plus 2 epsilon prime P minus 2 bracket close epsilon prime P divided by 3 delta minus 1 epsilon prime P plus 1. Here, epsilon double prime, that is loss factor, S stand for solid, epsilon double prime P, P stand for powder, delta R, another bracket, epsilon prime S upon epsilon prime P raised to 2 by 3 for dielectric constant, double prime upon single prime is less than equal to 1. Where epsilon prime S is the dielectric constant for material bulk, epsilon P, that is powder sample. Here, the experimental results have been verified with the values obtained from Boucher equations, that is these two equations, dielectric constant and dielectric loss. Now, the values of conductivity, loss tangent, and relaxation time are obtained by employing the following equations. Sigma P is equal to omega epsilon 0 epsilon double prime, and tau P is equal to tan delta upon omega. Tan delta is equal to epsilon double prime upon single prime. Here is the detailed structure of the per millet material, the values of wavelength in dielectric lambda d, that is d rho by dn. Here in first column, we have taken relative packing fraction, that is delta R 0.897, in second 0.966 and 1.00, it is called as solid bulk. At 20 degrees Celsius, the lambda d, that is the wavelength in dielectric, that is in centimeter, is 1.920. D rho by dn is 0.120. At 35 degrees Celsius, lambda d is 1.94. and d rho by dn is 0.117 at a 50 degrees Celsius. Lambda d value of lambda d is 1.952 and d rho by dn is the 1.103. Now, at a solid bulk, the value varies. Now, in this table, we have taken the temperature at 20, 35, 50 degree packing fraction, epsilon prime, that is dielectric constant for powder, dielectric loss for powder, tan delta, relaxation time, conductivity, and moisture content. Now, in the result and discussion section, dielectric constant and loss, the dielectric constant and loss systematically increases with increasing the values of delta R. This is expected because with higher values of delta R, the interparticle endurance offered to compact medium will be much higher than for material consisting less bounded particles. Now, the relaxation time systematically increases with increase in delta R. According to Debye's theory, when polar molecules are very large, then under the influence of high frequency field, the rotatory motion of molecules of system is not sufficiently rapid to attain the equilibrium with fields, and due to increasing hindrance to the process of polarization. uh, the second thing is conductivity. Conductivity systematically increases with the increasing delta R. It suggests that at higher compactions, there is no micro cracks developed in the sample due to high mechanical pressure. The last is the reference section. We have taken the references from Bansal A.K. Singh, PJ, Sharma K.S., micro dielectric measurement in different varieties of rapeseed, mustard seeds, Indian Journal of Pure and Applied Physics, uh, Gandhi J.M., Jangid R.A., Bhatnagar, Indian Journal of Pure and Applied Physics. So all this was the postal presentation. Uh, Thank you. 5 मिनिटात झालं का?